In organic chemistry, we often deal with molecules that have multiple functional groups, and sometimes we would like to do a reaction on one of those functional groups while sort of leaving intact the other functional group. Sometimes this is not possible without the use of a protecting group. Some of these functional groups may get in the way of a reaction that we want to do in the molecule. So one of the tricks to performing reactions in molecules with multiple functional groups is to protect one of those functional groups, in other words, hide it and perform the reaction on the desired functional group. As an example, in this molecule, we have an alcohol and a halogen. And if we wanted to convert this halogen into a Grignard reagent by adding magnesium and theoretically form this Grignard reagent, one of the things that's going to happen is once we form the Grignard reagent, it would react with itself. Since the alcohol is acidic, the acidic hydrogen would protonate the carbon where the Grignard is found, and therefore form an alkane or add an extra hydrogen on that carbon instead of remaining as a carbanion. When it comes to alcohols, one of the ways we can protect them is by using Silyl protecting groups. In other words, attach a silicon to replace the hydrogen on the alcohol. The simplest Silyl protecting group is called TMS. TMS stands for trimethyl silicon, and we can add it by using TMS chloride. Alcohol that reacts with TMS chloride and a small amount of base, such as triethylamine, would be converted into a TMS silyl ether. In other words, the silicon is attached to the oxygen, and then we would have some sort of alkyl group here. This is a form of a protected alcohol. As an example, this secondary alcohol, when reacted with TMS chloride and triethylamine, would be converted into a TMS silyl ether as shown here. One of the most common ways to remove a TMS protecting group from an alcohol is by using a fluoride source. The most common fluoride source for these types of reactions is tetrabutyl ammonium fluoride, or TBAF. TBAF has a fluoride source, or is a fluoride source. That fluoride can then attack the silicon and replace it eventually with a hydrogen from a acid in a second step. So the mechanism will occur as follows. The fluoride would attack the silicon, and then the electrons from this bond will go towards the oxygen, forming this oxonium ion, which would then be protonated by acid to form the alcohol. The driving force behind this is the fact that we're going to form a silicon to fluoride bond, which is one of the strongest bonds in chemistry. This is how we would remove a protecting group that has silicon on it. One of the disadvantages of using protecting groups in general is that it adds two steps to a synthesis. So we would always have to put on the protecting group, and then once we have done the reaction, the required manipulation that we want to do, we would have to do a step where we remove the protecting group. Of an alcohol that also contains a bromide, and if we wanted to turn that bromide into a Grignard reagent, we would first have to protect the alcohol as a solid protecting group. So if we add TMS chloride and triethylamine as a base, we convert that alcohol into a silyl ether. In a second step, we can convert that bromide into a Grignard by adding magnesium. Since the oxygen is protected now, it no longer gets in the way of doing this reaction. In the third step, we would then use that Grignard reagent to do some sort of reaction, for example, adding to an aldehyde to form an alcohol that has this long carbon chain plus the protected silyl group attached to it. In the last step, we want to now remove the silyl-protecting group by using TBAF, expose the alcohol we have here. And so overall, we have used a step to add the protecting group, a step at the end to remove it, and in between, we could do the manipulation we wanted with the Grignard reagent without having to worry about the alcohol getting in the way of the reaction.